Can everybody hear? Awesome. Let's begin. So, hi everyone. Today's tutorial is named Deep Learning Practitioner's Toolbox. And before we begin, just a few announcements. So, all right. So, I suppose that most of you have submitted by now your project proposals because they are due today. And in the following days, we will review your project proposals and give you a green light to start. And again, this review process is generally meant for you to make sure that you're on the right path, that your project is feasible, and maybe if we'll have more things to refer you to, then we will let you know. So now that you've all handed out your project proposals, I suppose that some of you may feel like this. And actually, the purpose of today's tutorial is to alleviate some of your fears regarding the final project, especially in the technical manner. So today we will be discussing several tools, several techniques that could be very helpful for you during your projects. Most of the techniques are universal, but some of them may be more relevant to some than others. So in a nutshell, today we'll be discussing Torch Hub and hooks, which you should be familiar of from the homework. Later, we will discuss TensorBoard, some transformations, and two very important topics, in my opinion, reproducibility and saving and loading models. But just before we begin, before we dive in, if there's one thing that I'd like you to take from today's tutorial is to not reinvent the wheel. And by this, I mean that you have a very relatively short amount of time to do your project. And in your projects, you'll find yourself handling a lot of technical stuff, but our main focus that we want you to focus on is to take the project as a research project. So try not to reinvent the wheel, not to implement from scratch things that maybe other people have done before. And before you start implementing entire new models, just take a quick look at Google or in the internet and see if someone has done these things before. And to be more relevant to today, we will discuss several open source tools that you may also consider using. Awesome. So let's begin with the PyTorch Hub. So PyTorch Hub is essentially a repository in a remote server in the cloud, so to speak, that belongs to PyTorch. And in this repository, you can find a plethora of pre-trained models from all sorts of tasks and kinds that could be relevant to some of your projects. So let's take a quick look at how to use them. So first of all, you want to see which models are available for you. And this could be done using the Torch Hub list command. So all you have to give is the PyTorch Vision repo name as an input, and you receive the list of all the available models. And actually, besides the default PyTorch repository, there are also other repositories that are hosted by different research groups that could also be relevant for you. So you're more than welcome to explore this. Then after you've chosen the model that you want to load, for instance, in our case, Resonance 18 model, then all you have to do is use the Torch Hub load command, given the current repository and the name of the model you want to use, and of course to specify if you want it pre-trained or not. So in this case, we're actually loading a Resonance 18 model, which is pre-trained on ImageNet. And then finally, when you have the model, it's pretty easy to use. You, of course, need to set it to eval in case you want to use it simply for inference, and then you can just define an input, pass it through the model seamlessly, and receive an output and work exactly the same way as we have until now. So this is a very powerful tool that I really recommend you to explore for your projects. And in fact, you could also have used it during homework 4. Now, after we're done with Torch Hub, let's briefly discuss hooks for the sake of completeness. So we use models in deep learning, and during training or inference, we find ourselves doing a lot of forward passes and backward passes. And actually, sometimes we want to to be able to examine what's happening within these processes. And this could be done by hooking, by registering specific methods to either the forward pass or the backward pass. Today, for simplicity, we'll only see how to register methods to forward passes, but doing it for backward passes is equally simple. So let's take a look at how we register a hook. So assume we have some method named myHook. It has a very specific signature. So all the methods that can be hooked need to have this exact signature. So they receive the module that they're about to forward or backward pass, the input to the model, and the output to the model. And then in this pretty simple hook, all we do is we print the input and the output shapes. And the way to register this hook is to choose the exact module, the exact layer that we want to register our hook to. And then we invoke the register forward hook method, and we give the method as an argument. So for those of you who are less familiar with PyTorch, this could be untrivial, right? This is a method, but we still give it as an argument to this register forward hook method. And then later, once we implicitly do a forward pass, then the hook is invoked on the relevant layer, and it indeed operates the way we expected it to. So the same way that we can, any questions? Sorry?
Can you maybe pinpoint the point about passing the method and not an argument? Like, what is the difference between calling this and this?
Oh, sure. So we will also later have another example that has to do with these stuff, but maybe it's best to discuss this now. So as you see over here, we're simply passing the name of the method. So in Python, all the objects that we have, including methods, including variables, they are all considered as objects and could all be, to say, treated as variables. So here we simply pass the method itself, not its output. We're not invoking it. We're just telling the register forward hook to invoke this method when needed. And if indeed, as Shai previously wrote, we would have written the parentheses and the inputs within them exactly this way. So that would have meant that my hook has happened. So this printing would have occurred, and then only its return value, which currently is none, because in this specific hook we're not returning anything, only this return value would have been given to register forward hook, and this would result with an error because register forward hook doesn't know how to handle non-objects. I hope this is a little more clear now. And if not, so really you can stay offline and ask me more about these stuff, because these are very Python related discussions. Anybody else? Any questions? Awesome. So we've seen a way to register a hook, and similarly, we might also need to remove hooks. So over here, we again register our method as a hook to this layer, and the output of the register forward hook method is a handler. And then later we can simply invoke the remove method of this handler, and the hook is unregistered. So this method will no longer be invoked once reaching the forward pass of this layer. So if indeed we do a forward pass on the entire network, nothing will be printed because the hook will be uninvoked. And now we'll see a simple example, a slightly simpler example than what you had to do in homework 4, for how to use Torch Hub and to use hooks in order to do feature extraction. So indeed, we define a module, a class named feature extractor that receives a model. We save its private members, the feature which is currently none, the feature which we want to extract, and the model itself. And then we define this method. So here is the slightly tricky part related to Python, so pay attention. We have this method, getFeatureHook, which inside of it defines the actual hook method. So you see that the signature of getFeature is module input output. As we said, that signature of hooks needs to be defined. So this is the actual hook, and what the hook performs is it addresses the inner member of feature extractor, the feature member, and assigns the output of the feature to be inside self feature. So actually, our hook method addresses self members of the class. And in order to do this without specifying self, without specifying get feature as a class method, we have to sort of wrap it with an outer method, which is a class method. So this is something, again, that if you're not like very fluent in Python will be a little untrivial, but this is at least the most comfortable way that I know how to do this. And then it actually enables you to address the inner methods or members within the hook without changing the signature and still make it a hookable function method. So now that we have the get feature hook method, we want to register get feature to some relevant layer. So this is done by invoking, again, register forward hook. But here we're not invoking it directly on get feature because it wasn't defined by the class. We're invoking it on the output of get feature hook. So as Shai stated before, here we actually see these parentheses because we're invoking get feature hook, and it returns get feature, the method itself, not its invoking. Is this clear? I will take that as a yes. Okay, and of course, when we delete our feature extractor, we want the model that we received as input to be free of hooks. So we simply remove the hook using the handle that we had from the registration point. And of course, if we want to call the feature extractor itself, then we receive some input, we pass it through the model, then the registered hook, the one that we called here, is called. It places the relevant feature within self feature, and then we can simply return this member, and everything is self-contained and functioning properly. And the way to use this feature extractor is simply to define a model. We can, again, easily do it using Torch Hub. Then we define our feature extractor given this model, and then we define some input. It could be an image, it could be a random input, and we give it to the feature extractor and finally receive the intermediate feature we were hoping to receive. So I don't know in how many of your projects you wanted to do feature extraction, but in general, this is a very important and powerful tool, and this is a modular way to do it. Awesome. So let's continue. Until now, we've discussed Torch Hub and we discussed hooks. And now we'll start discussing things that have to do with monitoring our training process. So up until now in our course, we've seen only very simple and naive ways to monitor visually our training processes using live loss plot in both ZSSR and style transfer homeworks. And today we will learn how to use a slightly more sophisticated tool named TensorBoard, which is actually a tool created by TensorFlow. So it wasn't originally made for PyTorch, but since it's very popular and ubiquitous, so we decided to show you how to use it for PyTorch as well. So first of all, assuming most of you will be using the Google Collaboratory for your projects, you need to do some very simple preparations in order to be able to use TensorBoard. So first you have to install TensorBoard. Then you have to load the TensorBoard extension because we need to use TensorBoard as a command in order to launch this beautiful user interface that we've seen over here. So we load the extension, then we do whatever we need to do. We train, we do inference, whatnot. And then finally, we can run the user interface within the Google Collaboratory by using the TensorBoard extension on some log directory. So in general, if you just use the default directory that you're on, it should work. But just to have a better understanding of what's happening behind the scenes, so actually TensorBoard has an object named summary writer, which when created, creates a a directory named runs. This could be overridden, but this is the default name of the directory. And within this directory, it creates a subdirectory that defines the current run that you're doing, the current experiment that you're running. And within this directory, it holds some file named events.out.tf events, which contains everything that you're going to log with TensorBoard that we will soon see in the following slides. So actually, everything that we're logging is saved to the disk. And this is the reason we have to state some logging directory from which we want to load the TensorBoard. And this is very powerful because this means that even after we're done doing everything, or even if our script for some reason failed in the middle of running, we still have these files to see our training process. So this is a very powerful thing to use in your project. Awesome. So now let's see how we use the summary writer in order to log and monitor a bunch of cool stuff. So the most simple example is to log scalars, which is of course very relevant to us. For instance, if we want to log our validation loss or our training loss during the training. So this is done by invoking the add scalar method. And then we get these really visually appealing graphs. And of course, using TensorBoard, you can zoom into them, you can smooth them. So it's very comfortable to use. And instead of only saving losses on a specific tag, you can also save other tags as well. For instance, in this case, train accuracy and validation accuracy. And these are saved in different tabs. So TensorBoard quite conveniently allows us to organize all of the relevant scalars that we need for our training process. And another cool thing about TensorBoard is that if we do several runs, if we try to train our models several times and we want to compare between the runs, then it simply saves a different file for each one of our runs and shows, this is all done defaultly, so it just shows each one of the runs in a different color. So then we can examine all of our runs together and quite easily see which one excels in each scalar. And of course, if we have too many runs and this becomes too overwhelming to see at once, then we can toggle our runs as well. And finally, when indeed people use TensorBoard for their projects, this is one of the TensorBoards that are hosted in TensorBoard's website. So you can see that they save a ton of metrics, and they save them all organized, and it's easy to see the difference between the runs. So again, this is a very powerful thing to use. But in TensorBoard, we can also log other things that are not scalars. We can also log images, for instance. So one very useful thing to do, in my opinion, is when you're trying to train a model on batches of data, it's important to log the batches, or at least the first one, in order to get the sense of the variability of what your model is receiving. So this is, for instance, from the FashionMnist example that we've seen in the previous PyTorch tutorials. So here we first fetch some batch of data from our data loader, and then we create a grid, an image, which is a grid of all the images that we had in our input, and then we simply use the add image method in order to log this image. And of course, you can log the first batch, you can log the batches every epoch, you can do whatever you like, and TensorBoard just shows all of this very conveniently. And besides logging images, we can also log figures. So it's practically the same thing, only here we invoke a slightly different method. So if you want to create more complex figures than just images, this is the way to log them. And besides images and figures, we can also log graphs. So in this example, in the FashionMnist example, we're actually using a relatively simple model. If you remember, it's just an MLP. But in your project, you may find yourself using more sophisticated models that have residual connections, or maybe even GANs that have like several backbones. So it could be kind of useful to visualize this graph and make sure that it's created the same way you expected it to. So if we visualize the graph here, we can see the input and the output, and even the shapes of the input and the output, which is very convenient for debugging and understanding what's going on. And if you press on one of the modules, then you can see them open and you can see their visualization recursively. And this could be done, again, for the linear models, et cetera, et cetera. So this is also a very convenient tool, in my opinion, at least for debugging and for understanding the shapes of the inputs and the outputs to the different modules. Another cool feature that TensorBoard gives us is to plot histograms. So one of the useful use cases of plotting histograms is to plot our weights and our gradients in the different layers in our models across training. So we can do this pretty simply using this code snippet, and then we receive these histograms. So each histogram presents the histogram of the weights of the fifth layer, or the weight or the gradients of the fifth layer across time. So then if we have issues such as vanishing gradients or exploding gradients, we could visually see them using these histograms. So again, this is another great tool that will allow you to understand what's going on in your training process. And finally, the last feature, which to my opinion is actually most useful, is to log hyperparameters. So when we do our experiments, when we develop some deep learning model, we often find ourselves trying to use different hyperparameters or different configurations, and we want to see how they affect the metrics that we care about, such as the loss or the accuracy. So whenever we run an experiment, we can log its relevant hyperparameters, for instance here, the learning rate, or the batch size, or the epochs, and the relevant metrics that we want to monitor. And then after we've run several experiments, we can see all of the relevant hyperparameters and values in this very convenient table. And for those of you who are less table persons, then you can also see this in a convenient diagram. And this is actually a useful visualization, because from this it's very easy to see that, for instance, if we use a very low learning rate and a very small batch size, then we have a great decrease in our final performance, in our accuracy on the validation set. So examining these diagrams given to us by TensorBoard allows us to understand things about the hyperparameters that we choose. Any questions until now? All right. So once again, as I've told you in the beginning of the tutorial, don't reinvent the wheel. You have great visualization tools to use, and you don't need to create them all by yourself. And I really encourage you to use them. So besides visualization tools, we also have other tools for other things that we find ourselves needing to do in such projects. So now we will cover the Augmentations library, which is mainly used for augmentations. So there are many augmentations that we might find ourselves needing to use that aren't available in PyTorch, and that's what Augmentation gives us. So of course, it also gives very simple augmentations such as cropping and flipping and adjusting brightness and contrast and etc. These sort of augmentations that we use for classification or representation learning tasks. And the syntax is very similar to torch vision transforms that you should all be by now familiar with. So the only difference is the import that we do. We import augmentations instead of torch vision. All the rest looks just the same. But augmentation also offers us unique kinds of augmentations. For instance, for object detection. So if any of you are doing object detection related projects, then you can create augmentations on the data sets that you wanted to use with bounding boxes very easily. So again, the syntax is simple. You simply define the transform that you want on your bounding boxes and on your images, and then you receive the output seamlessly. And besides object detection, there are also key point detection augmentations. So you see different images, but still the key points lie on the same places as before. And it even knows to remove redundant key points that don't exist in the image. And also for mask segmentation. So if any of you are doing segmentation related projects, this could be relevant to you. And besides Augmentation, there's also another useful library you might want to be familiar with that's named korina. And korina also offers augmentations and different types of low-level computer vision operations, but the main difference between korina and augmentation is that in korina, all the operations are fully differentiable. So you can use them not only as augmentations, but actually within your pipeline, within your deep learning pipeline. So if you want to do a forward pass and a backward pass through any of the following augmentations, then you can of course do so. So first of all, you can use perspective transformation. So if any of you are doing geometry related projects, you have source and destination points that have correspondence with each other, and then you can simply find these points and warp your images to the relevant destinations. And again, you can use this inside deep learning pipeline and not only as an augmentation. And there are also other methods such as canny edge detection, such as Gaussian blur, and sharpening and unsharpening masks. So you might want to look around at these two libraries and maybe find more libraries for yourself and see if any of them already implemented things that you might want to use in your project. Anything until now? Okay, so now to our final two topics. Let's discuss reproducibility for starters. So by this point in the course, I think that most of you have some experience with training models, and you might have found yourselves training a model in a specific configuration and receive some loss curve, and then going away for a moment, coming back, trying to run the exact same thing and receive a completely different loss curve. And at this point, most people start to ask themselves, what's going on? Do I have a bug? Maybe I did change the configuration. So the answer to this is your code was probably written in an unreproducible way. And one might ask, what do I mean by reproducibility? So does anyone have any idea what parts of our deep learning pipelines could be prone to reproducibility issues? Sorry, I didn't hear that.
When you initialize the weights, you need to define the seed.
Okay, so that for instance. Anything else? Any other ideas? Okay, so I guess I'll just show them to you. So like Michael said, we indeed need to initialize our seeds because in our deep learning frameworks, we have to do a lot of things with randomness. So whether it's initializing our weights, whether it's initializing our data loaders, and even some of the actual layers that we use have some randomness within them. So it's important to initialize the seeds. The actual random operations that we're using are not purely mathematically random. They're actually pseudo-random. They rely on some seed, some integer, for instance, in order to create a random sequence. And if we use the same seed, then they produce the exact same seemingly random sequence. So we choose some seed, for example, and we have to initialize all the libraries that we are using. These are the most common ones. I think it's very unlikely that you'll use others. So we have to initialize these seeds. But sometimes this is not enough, and we still receive different results for the same runs. So there are other things that we can do in order to make our code more reproducible. So one thing is to use deterministic algorithms only. So when trying to understand how exactly the different algorithms that we use are implemented, such as the convolution algorithms or the batch norm algorithms, so apparently some of them are implemented in an undeterministic way, which means that we can run the exact same thing on the same input, but still receive different results. So we can set this flag to be true, and then we ensure that all the algorithms that we use are deterministic. But the disadvantage of doing so is that sometimes it costs in performance. So we might slow down our training process or even our inference process. So another thing we might find ourselves needing to do is to set the torch backend cuDNN benchmark to be false. And what this actually does is when we use convolution operations on a specific size, like on a specific shape, so what CUDA usually does is it runs some benchmark of several available convolution methods, so different ways to compute the convolutions, and it chooses the one that runs fastest on this specific machine. And that means that if we run our code on different machines, then we might find ourselves having different results. So if we set this benchmark to be fast, we're actually not allowing CUDA to choose different algorithms, and we ask it to always use the same one. And again, the disadvantage here is we might have a decrease, a drop in performance. And besides these things, there's also one more thing that's very important to do in order to get reproducible results. And that's to not only set the seeds of our, like our main, but also to set to fix the seeds of our workers in our data loader. So just to make a quick recap, when we want to load batches of data, we have to use the data loader class, which sometimes when we have a lot of data and we have a lot of referrals to the disk, then we use several workers. So there are actually several sub-processes that are being opened in order to fetch our batches of data. And in fact, when you look into the data loader's source code, then you realize that it initializes the seed of each of the workers differently. And again, this is bad for us because this means that we can do the exact same run with the same learning rate and the same batch size, but the batching process will be different. And this is especially bad if we're logging our batches and we want to compare them across runs, but if we don't have the same batches, then we don't have the ability to do this. So the way to fix this is to define a generator. So a generator actually generates random sequences and to set its manual seed, and give this generator to the data loader. And then what this generator does is it creates a different initial seed for each one of the processors. But again, since the seed of the generator is constant, so it will always generate the same random seed for the different workers. And then in each one of the workers, we have to define again the same seeds for all the rest of the libraries and not only for PyTorch. Any questions so far? This might have been very technical, but I think it's important because these are actually problems that happen when we do projects. Anyone? Okay. So to our final topic for today, we'll discuss saving and loading models. So again, you're doing a project and you're training something, and then you want to use your model for inference, and sometimes you want to do your inference on different scripts, and this could be a problem because up until now we've only seen how to train models, but we haven't seen any way to use them outside of the code that we've trained them. So conveniently enough, PyTorch gives us two methods. One is called torch save and one is called torch load. And what these methods do is they serialize any type of objects, not even just models, also tensors and other PyTorch objects. They serialize them to the disk. So to torch save, we can give some objects and we can give the path to which we want to save it, and then simply we can load it the same way. And the most trivial way to save and load models is to serialize the entire model. So we take a model, we train it, and then we simply save it and load it when it is needed from that path. But there are problems doing things this way. Can anyone guess any potential problems? Anyone?
We need the architecture of the model.
Yeah, that indeed could be one of the problems. So the advantages of doing this is that it's very simple. It's only 2 lines of code. But 2 disadvantages is that we can't change the model class once we've saved things this way, because here we save the model using the exact class that we've defined in order to train the model. And during development, during research, we find ourselves changing the classes quite often. And then if we save the model and we just serialize the same class and we don't have the class that we used to do the serialization process, then we can't load it. And then you might find yourself in a case that you've trained many models, but you can't use them anymore, and you don't even remember in what version of your class you saved them. So this is indeed a very bad thing that can happen. And another disadvantage is that we can't continue training from this point because we lack some of the data, some of the state of our objects in order to continue training. So if some of you are working with the Google Collaboratory and you're doing some training and then the Google Colab shuts down and you want to continue training from this point, you can't do it if you save your models in this way. So conveniently enough, PyTorch gives us a solution for this. So given a model and given its weight or its state, given the parameters within it that change during training, we, instead of saving the entire model, we save the state dictionary of the model. So just to make sure we all understand what a state dictionary is, so given some class with some parameters, with some layers, we initialize an instance of this class. So its state dictionary would be all the weights of the model. So everything that could change during the training process is saved in the state dictionary. And then we can save in a better way, in a more robust to changes way. So instead of using save and load directly, we use the load state dictionary method. And what it does is it receives the object that we want to load. It receives the state dictionary and it loads it to the model. And then what we actually do is we don't save the class, we only save the state dictionary into some path. And then later we explicitly create the class that we need, and then we load the state dictionary. So we first load the state dictionary from disk, and then we load it into the model. And again, here, this means that you can change anything in the class besides the actual parameters, which is very strong, because if you want to add more methods to do fetching or some sort of stuff, then you can still do it without having to leave behind all of your pre-trained models. But I still haven't answered one thing. So we know how to save and load models in a way that's robust to changing the class, but we still don't know how to do saving such that we can later continue training. So we actually want some sort of checkpoint. We want to save a checkpoint. And what's missing is that not only the model has some state dictionary, so also the optimizer has some state dictionary. So as you can see over here, if we look at the SGD optimizer, for instance, it has a learning rate, it has momentum and weight decay, so all these other stuff that could potentially be changed during the training process. So in order to save everything we need in order to continue training, what we have to do is save an entire checkpoint. So we actually save a dictionary consisting of the model state dictionary, the optimizer state dictionary, and also other relevant things such as the current epoch and the current loss. And we save all of this to a checkpoint path. By the way, I haven't said this, but PTH or PT are the conventional suffixes that we use when we save PyTorch related objects. So we save this entire checkpoint. And then later, when we want to load it in order to continue training, so all we have to do is explicitly state the model class and the optimizer class. Then we have to load the entire checkpoint. We have to load the state dictionary for the model and for the optimizer from the checkpoint. So you see, we address the relevant respective keys. And of course, set the epoch and the loss and any other things we need to continue training fluently. And again, this is very powerful because then you're not restricted to the amount of resources or the amount of time that you get from Google Collaboratory or from any other external resources. And I actually recommend you to do this entire process every epoch or every fixed amount of time or so. So even if for some reason your process fails or stops in the middle, then you still trained something and you haven't lost your progress. So I really encourage you to do this in your project. Okay, so to summarize, I hope you've got some relevant tools for your project today, and you are less fearful for starting to work on them. And remember, you got it, you know what you're doing, just go right ahead and start working on them. Great, and next week we will be discussing implicit representation. Mirav will be discussing them. Great, thank you.